Good morning, everyone. I'm Yijing from Wisconsin Madison, and I'm going to introduce a framework for analyzing spectrum characteristics in large spatial-temporal scales. It's a joint work with Varun Suma and Domenico from iMedia. In this talk, I will first explain the motivation and challenges, then the system design. Next, I will summarize main evaluation results and finally conclude with some new insights from this work. The fundamental assumption of previous spectrum measurement and data analysis work is that there exists rich prior knowledge of spectrum utilization. People usually use some channel allocation information and rules enforced by regulation authorities, so they only record some power of each channel. However, as this figure shows, different types of signals on the same channel cannot be differentiated if we are only given the sum power. People also use simple assumptions to guide their measurements. For example, it is usually assumed that up to a predefined distance, two locations have a similar channel utilization pattern. As a result, previous work usually places sensors in lattice, as this figure shows. However, two locations within the predefined distance may actually not close enough to maintain the similar channel utilization pattern, for example, due to the blockage of buildings. So in our work, what we assume is that we have little prior knowledge. Given little prior knowledge, we collect a wide-band, fine-grained, large spatial-temporal scale spectrum measurement. We mounted a spectrum analyzer on a metro bus, and it covered the whole Medicine City for roughly a year. The spectrum analyzer recorded 300 megahertz to 4 gigahertz on a 100 megahertz basis, and for each measurement, it has 26K energy readings with GPS info. As a result, we gather more than 1 terabyte raw data. The challenges to analyze this data are the following. First, it is high-dimensional data of huge size. Previous methods usually are not efficient and scalable on data of this type. Second, because we only record data when the bus is operational, the data we gather is bursty in temporal domain and uneven in spatial domain. As a result, we need to consider spatial and temporal domains together rather than separately. Finally, we assume little prior knowledge, so unsupervised learning and semi-supervised learning are more desirable than supervised learning. So we propose a general framework called BigSpec to analyze spectrum data in large spatial temporal scales. A user can efficiently enable various applications to answer his or her spectrum-related queries of interest. The core idea of our BigSpec is that we perform computations in dimension-reduced space that preserves signal features in addition to leveraging the standard big data techniques. BigSpec has two kinds of modules to form its data analysis pipeline, which is shown in this figure. On the left-hand side, we have application-agnostic preprocessing modules. They offer a good balance between information loss and compression ratio. We use truncated SVD in frequency domain to reduce dimensionality and extract the useful features, and then compress the data accordingly. On the right-hand side, we have application-specific modules to answer specific queries from users. We build solutions for 3 applications, which are energy detection, spatial temporal spectrum estimation, and anomaly detection. Because our data is high-dimensional data, dimension reduction is critical. We found truncated SVD uniquely meets our requirement. We focus on the top K right singular vectors, or PCs, because they contain the information about how spectrum is utilized in the whole spatial temporal domain. However, the challenge here is how to determine the appropriate K. We use forward estimation and backward estimation correction to do that. Another question is how to interpret each capped PC. From this figure, we can see that the capped PCs can represent long-lived energies, short-lived energies, energy difference between multiple patterns, and energy shape changes. Based on the results from preprocessing modules, we build solutions for the 3 applications. For energy detection, there are 2 different kinds of spatial-temporal energies, long-lived energies and short-lived energies. We propose different algorithms to detect them respectively, and both algorithms work in the dimension-reduced space, so they are efficient. For spatial-temporal spectrum estimation, we use feed-forward neural network. Because its training process can be parallelized for multiple output dimensions, it has better scalability than state-of-the-art method kriging. For anomaly detection, we extend the definition of anomaly to 2 different domains, which are frequency domain anomalies and spatial-temporal domains anomaly. The main evaluation results are summarized as the following. For energy detection, we achieve 17 times more runtime efficiency compared with baseline k-means, which works in the original uncompressed space. For spatial-temporal spectrum estimation, we achieve sublinear scalability compared with linear scalability for baseline kriging. For anomaly detection, we can differentiate anomalous non-TV signal from legacy users that seldom uses a band in the same TV channel because frequency bin levels details are maintained. Through this work, we generate some new insights for future spectrum measurement and data analysis. For energy detection, we found spectrum utilization pattern observed does not comply with some of our prior knowledge. For spatial-temporal spectrum estimation, we found fine-grained spectrum estimation in large spatial-temporal scales can be hard, for example, for dynamic cellular bands. So we need a larger sensing platform of both static and mobile wideband sensors to get denser data in spatial-temporal domain and improve estimation accuracy. Finally, for anomaly detection, we found that anomalies can be caused by sporadic legal users. So in order to do illegal user detection based on anomaly detection, we need a unified platform that includes an accurate and fine-grained rule allocation database, as well as spectrum measurement and data analysis infrastructure. Thank you, and I'd love to take your questions.